Yay. And actually, I realized, Marcelo, I need screen sharing rights.
Sure.
Bye, everybody.
You should be able to share your screen.
Yay, okay. Share. Cool. Okay. Hi, everybody. Welcome back to what is lecture day 3 and lecture day 2 and neuroimaging at scale day 3, the final challenge, the exciting part, where we're going to try to discuss some. Well, we'll start with just recapping what happened during the assignment for those of you guys who submitted the assignment. And for those who haven't submitted the assignment, I did find out that you can submit it late and still get credit. So keep that in mind if you want credit for the assignment. And then we're going to go back and discuss DataLad a little bit more, just especially as it relates to some of the things we need to do for preprocessing. And then we'll talk about MRI preprocessing and the general steps that these pipelines tend to do. But more importantly, we'll talk about Docker and Singularity and container-based systems that we're going to need for preprocessing, how we're going to build and get those containers, how we're going to run them on Scinet, and how potentially at the end we'll talk about how to write them or adapt them for some of our own steps. Cool. So the first thing I want to do, was go back and wrap up or discuss some of the things in the BIDS conversion assignment that we did yesterday. So actually, Marcelo, we need to share Michael's screen now to do that.
He's supposed to be a co-host as well, so he should be able to.
Okay, yay. Okay.
Can you see it now? Let me see if I can try to make this bigger. How's that look? So yeah, I think, so for the people that submitted the assignment, some of you used the IXI dataset, and I think you guys were pretty okay there. And some people chose the BIDS tutorial dataset that we kind of went through together as a class. I just output kind of the solution for the BIDS tutorial dataset here. So we have our parent folder, a dataset description file, 2 top-level files, one for the phase difference field maps, and the other one's for the 2 tasks. And if you remember, the phase diff JSON just contains the the 2 echo times, and the task JSONs just contain the task name, the name of the task. And I think, so we also ended up going through the anatomical scans, the diffusion scans, and the field map scans as a group. I think where some people might have had some trouble with was the functional scans. So you'll see that we have 2 different scan types in here. One is the actual fMRI scan, and one is called a single band reference scan. So the way we can actually differentiate these, and I didn't really explain it yesterday, is if you just read the JSON file. I'm going to output 2 things. One is the series description, and the next is the protocol name. These are two fields that you should find in your DICOM headers, and they'll be saved to this JSON file. So for the series description, it looks like the fMRI scan has this func_task-bart name, but for the SBRef scans, it has SBRef in the series description, but not the protocol name. So what single band reference scans are, they're kind of they're scans with higher SNR and contrast. And so what these are used for typically in fMRI pipelines are to do head motion correction. For fMRI scans, what happens is a lot of the slices and the volumes are acquired really quickly. So it really helps to have a high contrast scan in order to do that head motion correction. Did anybody else have any other questions or kind of difficulties that they experienced with the assignment? I think in the beginning we had some permission issues, but that hopefully that got solved partway through. Yeah, I think the most difficult thing is probably trying to understand what data you have. It really helps if you have maybe a PDF of the scan parameters and you know, what the series descriptions are and the protocol names. But if you kind of go in detail through the bit specification, you'll get more of an idea of where the relevant information is and where you have to start looking in order to format your data properly. So yeah, I'll hand it over to Aaron.
Sharing screen too. Okay, thanks, Michael. So the first thing I wanted to talk about today, wait, I need to move my cursor over here. Okay, was to, we spoke about DataLad when we went through the notebooks, and we had some questions about it. I wanted to actually come back to it because I find it really useful for preprocessing and really useful for working with public data. And I wanted to speak a bit more about that. Wait, I'm gonna grab. Sorry, you can find the chat. Okay, I'm gonna make sure the chat is open on the screen. Okay, so one thing I wanted to talk about is that one of the reasons why DataLad exists or that the main DataLad people did was they actually started creating these records of what are public data sets. So if we actually open up this link to the DataLad repositories, it shows you a link of, and it looks pretty obscure now, but these are all actually links to different DataLad data sets of different projects that have made open data. And a lot of them actually, if you click on them, you should find that, yeah, there's usually a raw data bits folder. So you already have bits converted versions of these open data sets. So if you use DataLad to pull them, you can work with them right away. And you can see at the top, there's this command DataLad install. In this point, this // means it's in the public DataLad dataset, and this is the abide raw data bits. What I wanted to go back to speaking about was why this ended up happening. And that happens because some smart people started realizing that data sets are not actually fixed things. It sounds like a data set is a fixed thing, like when you go to publish a data set, you've collected all this data and you go to put it in a public repository, then you're done. But in reality, that's never true. In reality, you put data in a public repository and somebody finds out that, realizes that 3 of the scans were wrong and you need to fix something. And then you end up re-uploading those 3 scans. Or you realize that you haven't actually added all the metadata that people need to do an analysis, and you end up having to re-upload new data. or you're actually working, and in many cases for large data sets, this is the key. You're collecting a large data set over time, and there's different data release dates where more and more data is being added to the same data set, or more subjects are being added. So a bunch of people thought that actually what we need to do is start version controlling data the way that we version control code. So for those, actually, maybe I should ask in the chat who's heard of Git before, or who knows about using Git for version control. We get a yes or a no. Yep, okay. Cool. Okay, so we get a lot of yeses, but a few no's. I'm gonna actually go back to, instead of speaking specifically about Git, I'll speak about GitHub, which is a useful way to think about Git. And we'll come back to it pretty fast. So especially with code, especially when multiple people were contributing to code, we realized we needed a way to figure out how code was changing and evolving over time, especially when there's multiple authors. So a while ago, this concept of version control started, which is like tracked changes on a Word document, but kind of on steroids. So if we go to something fancy, actually, I might as well just go straight to something like fMRIPrep, which will, okay. Yeah. No, I don't. Okay. You can see it gets contributed to by multiple people over time, but you can also see that within, if you go into any one file in fMRIPrep, nope, this one had nothing in it. Let's even just go straight to the README file. README. And you type something called blame. You can see how many people have touched this one file at different times. And Git is something that allows us to do that. It allows us to know for every single line, actually every single character within every single line, who's actually made that change, and when was that change made. And then code answered something called, what we call a release cycle, where different releases happen. You can see this. Can you see releases? Oh, and then there's something called a release cycle, which is a collection of changes get marked with a number, so that we can know how things change over time. So the people at DataLad decided that we shouldn't just be doing this for code, we should be doing this for data. So the software that this type of way that we track code is based on something called Git, which is a contract matching software. Is this? Yes. If you want to apply this to code, because Git actually tracks every single character, and tracking every single byte doesn't work as well for say compressed images or neuroimaging. We needed a slightly different solution, so somebody built something called Git Annex, which has a little bit of a more elegant solution where instead of just recording the files or character changes in files, it records things like download locations and hashes of files instead. And then the guys at DataLad decided to build something that was slightly easier to work with in Python on top of Git Annex to make files, especially neuroimaging files, because it came from a neuroimaging group, easier to access. So we go through the idea. So we talked about using DataLad in those notebooks. It's actually a kind of difficult thing to install, and we didn't want to just create a module for you because we wanted to point out that when you do install it, it has two parts. One is Git Annex, which you can load with module load Git Annex now on the Cynet system. But the second part is just a Python package that's pip installed. And if you're working with if you're trying to use another Python package for your for whatever analysis you're trying to do, then the DataLad could conflict with the DataLad Python package environment could conflict with the Python package environment that you want to use for your analysis. So you might need to just install DataLad into that package. The second thing you can do is actually build a DataLad Singularity container, and we'll talk more about Singularity containers as we go. But the DataLad Singularity container is posted to Singularity Hub. Okay, so we talked, this was an example that was in the notebook about installing OpenFMRI, the OpenFMRI data set that we were working with. So yeah, so DataLad install, it's literally very similar. It's almost exactly the same thing as git clone. And actually git clone will do the exact same thing in this case. But the key is what it actually ends up cloning isn't all of the data. We saw this before, it's the entire folder tree structure, and for the large files, it's the download instructions for those files, as well as something called a hash so that you can ensure that that download worked properly. To actually get the data, you have to use a command called DataLad get, which will actually pull the data, download the data for you. And we saw that example on Monday. So from inside the folder, we can get all the data for this subject by typing get subject. We could also do something more fancy, like by using string expansion. So any kind of bash command, if we can find a way to like list that file, we can also run DataLad get only on those files. This is very useful because then we can actually get, in this case, I'm going to turn off notifications. Sorry, guys. Okay. In this case, we have an example. Wait, I gotta move my cursor. Okay. In this case, we have an example where potentially you only want to work with the anatomical data because you're only going to run a free surfer. You're only going to do an anatomical analysis. So in this case, you can use star expansion in this case to get for some subjects only the anatomical T1 weighted data from the folder. And another key thing you can do with DataLad is, so get will download the data, but drop back. But DataLad drop will do the opposite of get. So it will actually delete the data and take you back to the state where you only have the hash of the download instructions and the hash of the file. Okay, so this is, oh, and then one key thing to remember, and I wanted to actually show this a little bit better, is that DataLad datasets are actually Git repos. So for the case of all of the data on OpenNeuro, actually we have this OpenNeuro project that just has literally all of the DataLad datasets, and you can Git clone them. Git clone, which is actually exactly the same thing as DataLad install, and then you can start using DataLad to get and drop the data. Are there any, oh wait. Oh, so I thought I had one more thing I wanted to say. But we'll come back to it. Okay. Are there any more questions about DataLad before I move on? Okay. So moving on from DataLad to BIDS preprocessing. So BIDS preprocessing, for the most part, or how it's designed, is to work with something called a BIDS app. There's a ton of BIDS apps out there. And BIDS apps were a really exciting introduction because they added reproducible workflows with a simpler interface that would work for most things. This means hopefully that once you figure out how to run a BIDS app to do one thing, you can run a BIDS app to do something else. So once you figure out how to preprocess your fMRI data, you might only need to change the name of the BIDS app in your scripts to be able to preprocess diffusion data or to be able to do something else. So also with OpenNeuro, so apps, there's a little bit of things. So actually the OpenNeuro and BrainLife, you can actually run some stuff online. Okay. Also, there are containers. So we'll talk about containers for the rest of this talk. But containers hopefully add for an easier install, because instead of figuring out how to build everything on Sinet, we literally have to just get this one file, which is the container, and that contains all of our software. And containers run on any machine. So I have a Docker running on my work laptop right now, which means I could theoretically run all of these things on my work laptop if I wanted to do that to my work laptop. And hopefully, because a lot of dependent software is contained inside one version number or one release that says it all, they make for a simpler way to actually report what's going on in our data. So they hopefully bring more reproducibility to science. And they kind of have the promise for us as newbies that if we organize our data according to bids, which is something that we were learning to do yesterday, all of our pipelines will run. We can hope. Okay, so this is it's an older site, but it has bids apps, and it speaks to what all the bids apps are and what the list of them are. So bids apps, I want to say, have a pretty that have one type of command line structure that you see across all of the apps. So there's always okay. There's always at the bottom this run the script. The second argument is always just the folder of the input data. The third argument is the folder for the output data. And the fourth argument is always analysis level. So usually it's one of two words. It's participant or it's group. So in that way, you have three arguments that you use for pretty much any neuroimaging pipeline. Oh, and this separates whether or not it's a participant level. So a participant level analysis means that you're going to run every participant separately. So you're going to run the analysis. So this is like a preprocessing pipeline, versus a group level analysis would be something that would bring all of the data from multiple participants together. Say like a group level statistical map. Okay. And this is not an exhaustive list. This was the first 30 bids apps that were published, and links to them. Some of my faves and the ones that are definitely the most frequent are fMRIPrep, which we're going to speak a lot about. And it will also be a precursor for the fMRI analysis with Python that we'll talk about next week. MRIQC, which is very useful for quality control. Siftify, which I'm just partial to because I wrote it, which is for surface-based analysis of functional data. But there's also bids apps for the FreeSurfer pipeline. There's the HCP pipelines workflow, and there's CPAC or CPAC, which is the nice CPAC, which is also a connectome or fMRI preprocessing pipeline. We're gonna talk about a few of them. The first is fMRI for fMRI preprocessing. Michael or Jerry, do you want to speak to this, or do you want to leave this to me?
I don't think Jerry's here, but you can go ahead.
Okay, so fMRIPrep is probably the most popular bids app. I feel like most people who actually first bid converted their data did it so that they could run this pipeline. And a lot of people in the audience actually might be here just to figure out how to run fMRIPrep. fMRIPrep, okay, does a few things. Is for fMRI preprocessing. Preprocessing need to account for things like that the whole head move. We have whole head images, but we just want the brain for our analysis. That the fMRI image and the T1 weighted image are not actually aligned to each other. The fMRI can get distorted by changes in the magnetic field. The participants move in scanners, so the fMRI image isn't actually even aligned to itself. And that there can be movement that actually influences the fMRI signal. And all subjects aren't, oh, and then the last thing is aligning subjects to each other. So we need to warp images to some kind of template or some kind of normalization. Okay, so the first thing that happens actually in fMRIPrep is actually preprocessing, not of the fMRI image, but of the anatomical image. So there's T1 weighted processing where you need to take the T1 weighted image, you need to extract the brain, and then you actually need to normalize it, so register it to some kind of a template. In this case, it's an MNI template. There's also fMRI preprocessing, where you need to take the raw fMRI, you need to actually extract the brain because there's stuff around there, so you need to make the rest of this stuff go away. You need to correct for motion, so you need to register the brain to itself. You need to also correct for susceptibility distortions. You can see this in this kind of little GIF. We talked about susceptibility distortions a little bit yesterday when we talked about field maps. But the idea is that the magnetic field actually can distort the real shape of the brain. And you can use different tools to try to get the brain undistorted and looking more like its actual anatomical self. And then there's alignment to the anatomical or T1 weighted data, and potentially transformation into MNI space. The last thing, there's also the concept of confound regression. So fMRIPrep doesn't actually regress confounds, but it calculates all of the numbers that you need to do confound regression. And confound regression is something that we're going to actually talk about how to do using Python in next week's class. And the thing is, you don't need to know how to do, so it used to be back in the day that we needed to know how to do all of these steps individually, and we had to write individual scripts to do every single one of these steps. But now with fMRIPrep, we give it our data and it figures out what it needs to do. And it runs these steps in a relatively intelligent way. Okay. So this is a diagram from the fMRIPrep paper of how all of those steps fit together, both an anatomical pipeline, which does the anatomy and also extracts the surface, as well as all these functional steps. Okay. So you get all of these different outputs, and actually the outputs are something we're going to speak about more next week when we try to work from this data. You also get all the cool surfaces. Okay. MRIQC is a second pipeline that we want to speak about, and this one actually has a very similar interface. So you can see I told you that there were three. So this is running in a Docker, but actually I'm going to hand it over actually to Michael. Wait, we have some questions first, and then actually we're going to hand it over to Michael. Okay. Okay, yes, so we're going to give the information to Michael because he's going to actually talk a bit about MRIQC and what the outputs look like.
So I actually ran MRIQC on the BIDS tutorial data from yesterday. So there's a single subject, but this is what the folder looks like. You have a subject folder. Oh yeah, one thing I should mention is that MRIQC outputs QC metrics and QC pages, but only for anatomical scans and fMRI scans. So if you're working with diffusion data, there's nothing really that does that yet, aside from maybe Eddie. But you'll see that it creates an anatomical folder and a functional folder with JSON files in each one. And so the JSON files contain all of the different QC metrics that it calculates. And if you want to learn more about what these different QC metrics are, you can check out the MRIQC documentation. They have a tab here called Image Quality Metrics, and they have different sections for the structural images and functional images that go into detail on what they're actually calculating, and the paper is that they used to back up their reasoning for using these metrics. But if I go back to the main folder, you'll see that once I've run the pipeline for each participant, I can run a group level workflow. And what that'll do is output two things. One is a spreadsheet with all the metrics calculated for each subject. And it's just easier to work with than the JSON file. And if in your analysis you wanted to filter subjects based on specific metrics, you could do that pretty easily. It also outputs an HTML file, and this just plots the different metrics. It's pretty interactive, so you can hover over each dot and see what the file is and what the measure is. So one of the things that we use quite a bit in our analysis, our data is the frame-wise displacement. So this is kind of a summary metric for participant motion. So you don't want this to be too high. I think the gold standard is 0.2 millimeters of motion on average. So this is 0.08, which is pretty good. And it also does the same thing for the T1s. Oops, sorry. It gives a group report for the T1s and T2s. These are going to be very similar. So what I showed back there was for each subject scan, it gives you this kind of individual QC report. So if you wanted to, you can even use these to QC your own data pretty quickly. So here it's just giving a montage of the actual scan, any background noise. And it also has this widget that you can toggle back and forth. And you can specify whether you want to include it or exclude it. And if you decide to exclude it, you can mark a reasoning why. And at the end of it, you can download all of these ratings as well. So it's really handy for creating kind of an interactive QC workflow. Anybody have any questions there? Cool. Yes, back to you, Erin. I think you're muted, Erin.
Okay. Oh, and share. Okay. And now I can actually go back, and one of the keys is that both fMRIPrep and MRIQC have a very similar interface, which means that if you figure out how to run one of them, you can figure out how to run the rest pretty easily. Okay. And just in our own analysis, we use fMRIPrep and MRIQC together for the most part because we usually want that extra quality data to incorporate into our analyses. Okay. One last thing, specifically, especially with fMRIPrep and MRIQC, we talked a little bit about that registration to a template space. This is something that also happened back in the day. They were putting all of those templates inside the Singularity container or inside the container, and then they realized that the number of templates as the project grew, they realized that they needed more and more templates to the point where they realized that the templates needed to go outside the container and they needed to reference them in a different way. So what happened was a project called TemplateFlow became born, which is actually another Git repo. But it's a Git repo that holds MR templates run by the people who developed fMRIPrep and MRIQC. So this is a DataLad repo that holds images of templates. So in this case, you have your MNI template. Hold on, TemplateFlow. We have say the MNI template, which gets aligned to by default in fMRIPrep, which I believe that this one has this crazy name. And then there's other different versions of the MRI template. This gets MNI template, this gets pretty annoying and or true that you realize when you actually try to combine across a lot of packages that they were all using slightly different versions of the MNI template, and you needed all of them to figure out how to reconstruct what was happening, which is why there's so many different versions of MNI here. But they also started adding some really exciting things like infant and pediatric atlases and things. I believe this is coming from the NKI, which is, so this is an older adult template, PNC, Philadelphia Neurodevelopmental Cohort. So they're starting to get a lot of different templates, and they're starting to try to branch out and think about templates that might be in non-human species as well. And to do that, because the number of templates was growing, they needed to put the templates outside of the container and use this TemplateFlow to be able to access them. Long story short, this was a good idea for them, but it becomes a little bit difficult for us on SciNet because the way this automatically usually wants to work is it's going to try to download the templates in the middle of a process. And in the middle of a process that when you're running your preprocessing, and actually on SciNet, this isn't going to work because the nodes where we preprocess our data, we don't actually have access to the internet. So one step before you start running something like fMRIPrep or MRIQC is to actually put the templates somewhere in your SciNet Scratch so that you can have access, so that it can just read it from those places. So this is an example of doing that using DataLad. There's another example of using the Python package that they have for downloading, which is actually more of just a wrapper for DataLad to do these steps in order to get the data. Okay. Second thing, now moving on to the exciting part. So the reason why we say that BIDS apps are easier to install is because they're containers. So containers are a weird concept. Can we get a yes or no answer of who's heard? Oh, wait, let me check back. Can we get some discussion in the chat about who's heard the word container before? Wow. Haven't heard of it, heard, not used. Okay. So yeah, we have the whole gamut. Some people have heard of it, some people haven't. So what a container is, in very simple versions. Okay, who's heard of the concept of a virtual machine, or a computer that you can build that exists inside another computer? Okay. Yes. Okay. So many people have heard of a virtual machine. A container is very, very similar to a virtual machine. And actually, when you're running a container on a Windows machine, you're actually using a virtual machine. But okay, so a container is a very simple, very, very similar concept to a virtual machine in that it has not just the whole, it doesn't just have, say, software. It has software, but it also has all the dependencies to that software going all the way down to an operating system or a container engine that's running on top of an operating system. So it's a little bit smaller than a virtual machine, but essentially we can actually think about it as a virtual machine. I think about it as a virtual machine. So there's two types of containers, two types of container software. The first is Docker, and Docker is very popular. And the second is Singularity. Okay. The reason, so this kind of comes the idea that when we want to shift software, there's, especially for fMRIPrep, it's not just fMRIPrep that runs. There's literally 10 gigs worth of fMRI preprocessing software, and every single one of those fMRI preprocessing software dependencies is an area where you could install it wrong, where you can install a different version, and it could work differently. So when you get fMRIPrep, you don't just get the code that runs fMRIPrep, you get all of those dependencies. And they do that by packaging those things into a container, which is like a virtual machine that you're going to run on SciNet. Okay, so these two types of containers, the two types of containers we have, there's a type of container called a Docker container or a container engine called Docker. And this is potentially very popular outside of the high performance computing world. It's got a very strong development community, and it has this thing called Docker Hub, which I will tell you about soon. It works on any system, Windows, Mac, or Linux. And it has this idea of layers, and those layers actually keep the size of individual Dockers smaller. So it's a bit smaller, it's a bit smarter when it comes to disk space than some things like virtual machines. The problem with Docker, which is a big problem and an absolute ending point when it comes to Sinet, is that it needs access to root. So you can't actually run Docker on Sinet. The administrators will never let you run Docker on Sinet. For that reason, we have something called Singularity. So Singularity doesn't need root access. We can get Singularity containers from the Docker specification, so building directly from Docker Hub, or just by converting a Docker container into a Singularity container. But the actual Singularity developmental community is a little bit smaller than the Docker one. Singularity Hub isn't used that much, and it only works on Linux. So in general, the take-home message is that in the community, we tend to write containers or develop containers using Docker or using Docker specification. But when we're working on Sinet or with any high-performance computing environment, we run containers using Singularity. So we use Singularity containers. Okay. So Docker and Singularity are pretty similar. And we might come back to this after we talk about running some things with Singularity to think about how to run them with Docker, or how to run them with Docker with Singularity. The key is that anything you can do in Docker, you can usually also do in Singularity. You just usually have to change a couple different commands in the flags. The flags tend to mount, so all the V's have to be replaced with B's. If you see instructions on a website for how to run something with Docker, you can usually convert it into a Singularity command. Okay, so building a Singularity container. There's actually, with the most recent versions of Singularity, which is the one that exists on Sinet right now, Singularity actually should exist on Sinet everywhere. You don't need to module load it. It should be there by default. Usually it's a simple command with like 4 parts. There's Singularity build, the name of the output, so just the path to the output, and the place where you want to build from. So in this case, we're building from a Docker Hub version of a Docker Hub recipe. So this is Docker Hub, it's the username, and usually on Docker, so Docker Hub, just like GitHub has Docker as a username, usually has the name, and usually there's a version code. So this is a Singularity build command that would build Singularity from, in this case, a program called NeuroDocker that was developed by this guy Kazmart, and this is the version. And yeah. Oh, and then the other way to build, and this might be a command as well, is that anything that you can build locally on your machine using Docker, you can convert into Singularity using something called Docker to Singularity. So this is one where this is an example of me building the same container as a Docker container on my local machine. And then right afterwards, you can run this command. It uses this function called Singularity where Docker to Singularity to actually convert it into a Singularity image. And then once you have that image on your local machine, it's usually not that big. You can usually just secure copy it onto the Sinet system. Okay. Another thing to know is that if you look at a lot of instructions on how to get Dockers or Singularity on your machine, you might see the word latest. This is kind of a go-to. is that usually most Docker or most Singularity versions always have a version that's labeled as latest. And if you just want the newest version, you can just type latest. However, if you're running something that you want to publish on, or if you're running a pipeline you want to publish on, you probably want to make sure that you're building with the exact same version number so that you have that recorded. Okay.
Sorry, Erin, can I just show an example of what that looks like?
Yes, yes.
So here's a list of the Docker containers for fMRIPrep. So you can see here they have the latest, which would, if you were on GitHub, this would be the main branch. And then Erin was also talking about different releases. So here you have tags for those specific releases. So as Erin was saying, it's best practice to pull from a specific release rather than using the latest tag.
Can you, sorry, while you had that open, can you actually show Singularity build in like Jupyter or something? Oh no, I meant like in the terminal. Or I can.
Maybe you can show it. I've actually never used Singularity build.
Okay, let me get. So I need an example of something to build, but I will find one. Okay. Okay, this is going to be a bit. Okay, so I'm in Signet. Like, can I? Okay. Okay. So on Teach, actually, if I run Singularity, so you don't need to module load Singularity. You should have Singularity anywhere. And Singularity build is pretty straightforward. So I'm going to just build something in my Scratch. So I can cd to Scratch paper clear. And I'm going to make service name. Okay, so I'm in an empty folder, and I'm going to find something to build. So Singularity build, one example. Oh, this isn't Singularity build, sorry. But one thing I can do is I can pull from Singularity Hub because the DataLad data is there. Oh wait, sorry. Yeah. Download, go, and then I've got ls. Yeah. So this line, Singularity pull shub. So this is Singularity Hub, DataLad, Dataflow master pulled DataLad as a Singularity image into this point in my Scratch. And actually then I should be able to run it. Yeah. And then I can actually run DataLad using that image. Another way to do this, I should do a smaller one, like NeuroDocker. Is if you go to Docker Hub, actually, I'll just do these examples because they're smaller. So I have a few Dockers that I've built. I built last week to create environments for a summer school. And you can see, wait, other view. And you can always see in Docker Hub, beside a Docker that you might want to pick, you can always see this command about how to Docker pull something. And we can adapt that command. Oops. When we go here. So, okay. I think it's Docker. Yeah. So in this case, it's a Singularity build, an image name, but it's actually building it from my Docker Hub recipe. Cool. Okay. So this is two different ways that you can get Singularity images onto site. And you can see happening. Okay. Back to my slides. Okay. Yeah. Okay. So that's how you can get a Singularity image. Now let's talk about how to run a Singularity image. When you run a Singularity image, the first thing to know is there's Singularity run, and then there's the name of the Singularity image that you want to run. And then after that, it's the arguments to whatever is the command in the image. So if this were DataLad, we would be Singularity run DataLad, and then the arguments that we would type after DataLad if we were running DataLad in the command line. Here's an example. This is an example with a larger pipeline. So this is my Siftify pipeline. And it's an example of just being able to print help. But we're going to add to this. So there's another thing, and we'll come back to how well this works. But sometimes it's useful to do something called clean ems. This is because in Singularity, usually a lot of things from the external environment, like environment variables, and especially things related to the way that Python runs for Python environments, gets pushed into the Singularity environment. So sometimes it's useful to use this clean em flag to not bring those environment variables into the container environment and keep things a bit cleaner. Okay. The other part, and this is the part that is difficult, is that Singularity images are like virtual machines. So we need to, because they're virtual machines, and Docker images especially, we need to actually usually tell them where data is. This is slightly different on Sinai, we'll come back to this. But the way that we do that is actually by using something called binding, or with this capital B flag. And what binding does, or the way a binding argument looks, is that it starts with a capital B, and then you have the path to what that data is going to be where that data is outside the container. So say this is some data that I downloaded in DataLad folder. So this is my bids data set. And then this is what the path is going to be inside the container. So you can call it bids input. So this is an example of actually running the Siftify pipeline using a Singularity call with two bind paths, binding input data and output data. So we created a place where we want the output to go. We're running the bids input. So we're binding our input data to a folder called bids input. We're binding our output data to a folder called bids output. This is our image name. So this is actually this whole thing, whole path to the image. And then everything afterwards, these are actually the arguments to the actual pipeline. So there's input file, output file, participant, because this is a bids app. There's always the arguments input file, output file, participant. And then the second thing I want to tell it is participant label. So if I didn't use this argument, it would try to run all of the participants in the data set, but by using the flag participant label, I'm telling it only to run this particular participant. And I'm telling it some additional flags like debug, dry run, and to only run the anatomical data, to not do the fMRI pipeline. Okay. However, in Niagara, you might see something a little bit differently, and we'll talk about this when we look at Singularity Shell. You'll see that actually, by default, any container that you run on Niagara will actually mount home, scratch, and projects in a way that makes them look like they are in home, scratch, and projects in your data. So you don't necessarily need all of these crazy bind commands. The second thing, this was back to binding input, right? Okay. The second thing is there's additional things that you might need to bind. So this is the case of binding. So for fMRIPrep and for Siftify, because FreeSurfer needs an academic license, and the developers of the pipeline wanted to not violate the terms of the FreeSurfer license, they actually asked that all of the individual users get their own FreeSurfer license, which is only a text file. You can get it in like a day from the FreeSurfer people if you do have an academic email address. And then you actually have to mount that. You actually have to give the location of that license inside the command in order for things to actually work. So this is an example of actually having the license. In this case, actually I have a license sitting in the course folder. You can bind that license to a location in the folder, and then you can call the location in the container where it is when it's bound. Okay. And the other thing is resetting home. So we find that sometimes the containers sometimes some particular pipelines actually try to write data to the home folder, and this is not very good. So we end up actually usually having to try to reset where the home folder is so that it doesn't actually get used so that the container doesn't try to write to it. So in this case, I'm changing the home folder inside the Singularity container to a random folder in my Scratch with this H flag, which resets the home. However, I found that for some other commands, they sometimes write a file that actually locks the processing, so you can't run multiple subjects at once, into the home folder. I don't know why they would ever do this, but one of them does. So in that case, I actually have been mounting a random temp folder into home in some of my scripts. Okay. Oh, and the last thing we can mount, because Sinet does have a burst buffer, which is actually really useful for small files, and fMRIPrep especially, and also MRIQC. A lot of these bids apps are actually written with in a type of programming interface that actually creates a lot of small files, and you might not want those, and they can really slow down the process. So to actually fix this, what we can do is write all those small files to the Sinet burst buffer. So we load the burst buffer. So we're binding the sign-up burst buffer, and we're actually making the workdir, which is the place where all the small files are going to show up, loaded to the burst buffer. And another thing to keep in mind is that another argument you can change when you're running fMRIPrep or Siftify is the number of CPUs that are going to be used for every participant. And it's good, I put this at 8. It's good to think about what might be the most useful for the subjects you have in order to use Synapse resources most effectively. Okay, that was a lot. Maybe we should pause and ask if we have any questions about what I just said. Oops, sorry, I did that just to see the chat. Okay, re-explaining the burst buffer part. Okay, so this actually is a very specific thing to sign at. So I'm going to put up Niagara. Okay, so Niagara, specifically SignNet Niagara, has this extra storage space they call the burst buffer. So the burst buffer is a space that I'm pretty sure you can actually only access within a running job, but it's meant essentially to work as a temporary storage space for files. It's much faster to read and write from. You're not supposed to leave stuff on there for very long, but it's useful for temporary files that you might want to look at later in order to figure out if something went wrong. So that's what makes the burst buffer actually really ideal for something called, for what MRIQC and fMRIPrep call a workdir. And that's actually where all the temporary files from the pipeline end up getting written to, as well as a lot of really small logs about whether or not certain steps completed. So the burst buffer is probably the ideal place to use for the workdir, so that you can, if a subject fails running, you can go into the workdir, you can figure out what happened. And then after the subject has finished running, you actually want to delete all of the files in the workdir because they're not actually the outputs that you want. But to make this work, when we talk about binding, we end up, so we want to set the burst buffer to the workdir, and in order to do that, we have to make sure that the burst buffer is accessed by the container using this bind command. Okay. Yeah, okay, this is actually kind of important. Okay, so actually I'm going to show this with, I'm going to show this to start with the one that I just started. Let's see. Actually, I might copy this one. Okay, so something really important, really useful for 2 reasons is something called Singularity shell. Okay. So in this case, sorry. Can you still see what's going on in the bottom here?
I think your screen isn't shared.
Oh, my screen isn't sharing. I need screen. Okay. Oh dear, I just realized I didn't actually share, but at least Michael shared the link to the burst buffer right up. Okay, sorry guys. Yeah, so fMRIPrep. Actually, I'll just run that twice. So in this case, I'm just setting an environment variable to this long path to my fMRIPrep image to make it a little bit easier to work with. This is actually a super old school version, but we'll talk about that. Okay, so Singularity. Okay, so what Singularity shell does when you run it, oh, that's not good. Maybe I moved it. Okay, let's Singularity shell one of these. Okay, so what Singularity shell does is it actually turns the terminal or the shell that you're working in into the Singularity container. So now my terminal is actually inside the Singularity container. So if I ls right now, it actually looks like I'm in the same place because if I go to the base, yeah. So if I go to the base, what I actually see is this is actually what the computer looks like when you're inside the Singularity container, which is actually slightly different than what it looks like when you're just inside it. But you can see actually, because of the way that SciNet works, actually, if you go to yeah, you can actually still see a lot of different files. So actually, you can use Singularity shell for two different things. You can, which one was this? Is the Jupyter I'm going. You can use Singularity shell for two different things. One is to do very quick tests to figure out why something in a Singularity container isn't working. Because these containers were built by somebody else, you can, once you're in Singularity shell, you can run commands as if they exist otherwise. So wait, maybe I'll show this better with the DataLad one. Okay, you can see that within this DataLad container, DataLad is installed at user bin DataLad. And you can use all of the classic DataLad commands without doing any like additional Singularity stuff in here. So this is a very useful place to go to debug what's going on in the container and to figure out everything that's mounted to the container. So I can figure out now that whether or not, say, something like echo scratch still works within the container. This kind of gives you a better idea of what's going on with the container and to be able to debug what's happening. It also gives you a place where you can do really fast things. So I could actually run DataLad pull or DataLad install from inside the container into my Scratch, and it should work. So this is useful, but it only works. So Singularity shell is really useful for debugging things, but it only works interactively, or it only works interactively. So on SciNet, you can't use it. You can only really use it on the head node. You can't do anything like super intensive with it. But the second thing you can use, which is very useful, is something called Singularity exec. So exec. Okay, I'm gonna type. I'm gonna get that back. Kind of a weird example, but okay. So this gives me the difference. So I should explain the difference between Singularity exec and Singularity run. So when somebody builds a container, they usually when somebody builds a container, so when the software developer builds a container, they usually pick one particular function or one particular command. In the case of fMRIPrep, it's the fMRIPrep pipeline that they want to make the thing that will run by default when somebody types the word run. They decide what that is and they build it into the container. Singularity exec lets you use any of the other software that exists in the container. So this is a weird example because the only thing in the container is DataLad. Oh, but I can do something like git annex. Because DataLad is built on git annex. Yeah. And I can type ahead. Yeah, okay. So because a DataLad container has to have git annex in it, then I can use Singularity exec to actually call help or to call git annex and not just DataLad. So a Singularity exec command has Singularity exec, the name of the image, and then the full command that you would want to run inside the image. This sounds okay. It sounds not that useful, but it's actually so useful because it means that you can use a container to do things, other things that exist within that container. So I mentioned that fMRIPrep actually has within the container so many different forms of neuroimaging software. So one of the types of neuroimaging software that exists inside the container. Oh wait, okay. One of the types of neuroimaging software that exists within the container is a software called FSL. And if you know FSL, there's a command inside FSL called FSL maths that you can use to say create a mean image. So if I want to use the Singularity container that has fMRIPrep just to be able to run something that contains FSL, just to be able to run FSL maths, I could do it in this way. So I run Singularity exec, I bind the data, and then I run FSL maths and I give it my whole FSL maths command. And in that way, I can actually do more with the container than just run the pipeline. So this brings me back to a concept like, which is maybe a bit controversial, which is containers versus modules. And when would you want to build a module to be able to run something like FSL, or would you rather just use Singularity exec with a container? I personally now am turning more to the idea of using Singularity exec because for the final reason, which is the thing I put as the third line, is that when you run module load FSL, or you write module load FSL in code and then you publish that code, is anybody else who doesn't have access to Niagara ever going to be able to run that code or ever going to be able to figure out which version of FSL you used and in which situation that code was? So will anybody ever be able to reproduce your result if it has a module load command in it? Hopefully, if it has a pointer to an image that somebody else can download and use on their own computer, they're much more likely to be able to reproduce your result exactly. It also takes a lot of strain off of, it's also good and bad, takes a lot of strain off of the people writing SciNet, because suddenly they're not compiling or building all of these modules for us. We're just moving images onto SciNet to run with Singularity, and they just have to make sure that Singularity runs. Okay. Oh, so this is the exciting part. So I talked about an example for running Singularity on one image, but we have a whole data set. We need to run a script. So actually, I'll turn the mic back to Michael, who might go over for a second some scripts that he's written to run some vids apps on SciNet.
Okay, let me just get them loaded. So here's an example of a script I have for fMRIPrep. So one of the, I guess, difficult things about running these pipelines on Sinet is that on Sinet, each node has 40 cores. And when you're submitting a job, you should try to use all of those resources available. Here's an example of a Singularity script. So I have the name of the job, some paths for outputting the output and error logs. I'm requesting a single node and then 40 CPUs for that node. And then here I'm specifying a time of 24 hours. So with fMRIPrep, I guess one of the longest things that it takes to run is FreeSurfer. So FreeSurfer is probably around 10 to 12 hours, depending on your data. And the fMRI part of that might take 5 to 6 hours. So I think 24 hours is a little bit kind of being on the safe side. You no longer have to load in Singularity or GNU Parallel, so I'm just going to get rid of that. But the first thing is I'm saving a couple of different things into my environment variables. So saving the bids folder. fMRIPrep requires a FreeSurfer license. So if you can pretty easily just get one just by going to FreeSurfer, filling out these details and downloading a license. And so what I've done is I've just saved that to my Scratch. And then I have the name of the Singularity container. And then here's another kind of thing that I had to do differently on Sinet. So as Aaron was mentioning earlier, we have to download the TemplateFlow templates to a folder and then bind that. So here I've saved the TemplateFlow templates using DataLad and then just bound it to this environment variable called Singularity env_TemplateFlow_home. And the next thing is I have my output folder, my work folder, and my temporary directory. And then this is the actual Singularity command. So first I'm binding all of these folders that I've defined here. So my temporary folder, my bids folder, my output folder, my work folder, as well as the template folder. And then here's actually where all of the fMRIPrep arguments go. So the way I found all of those arguments is by looking at the fMRIPrep documentation. So if you go to usage notes, it gives you all the command line arguments that the pipeline can take in. And so the default arguments are always the bids folder, the output folder, and the analysis level. So the only analysis level at this moment is participant. And then you can filter your data set based on specific participants if you only wanted specific fMRI tasks. You can even give it like a custom JSON file if you wanted to be even more fancy with your exclusion criteria. If you already had FreeSurfer run, you could pass it on to the NAT derivatives argument and then just skip that whole FreeSurfer process. Then there are some options to handle performance, different workflow configurations. So here you can specify which output spaces you want to use. So I think the default, if you don't specify anything, is using the MNI space template. But if you wanted to, you could output things in the FS average space or some other custom spaces like the T1 weighted space, the anatomical space, specific fMRI spaces. I don't really have too much experience with these spaces. I guess the common one is using the MNI space, so you might be fine just sticking with the defaults for that. And then, yeah, as Aaron was saying, I use the burst buffer as the worker, and then after my job is completed, I make sure to delete the work directory. The nice thing about fMRIPrep is it uses NiPipe, which is a Python package. And under the hood, NiPipe does a lot of really special things. So as it saves everything to the work folder, if by any chance your job gets canceled or if something happens to your job, you could restart it and it'll pick up immediately where it left off because you already have all the intermediate files saved in the work dir. The other nice thing is that NiPipe has some features that it can use to manage parallelization. So here I use the OMP and threads argument to specify that I want four concurrent processes to run within my job at the same time. And the other thing that I'm doing here is I'm feeding it a subject list. So what I tend to do for my analyses is I'll have an entire subject list, and then I'll just split that into separate lists using the split command. So here I'm just writing out a command to split it into several different lists, each with 80 subjects each. And then I'll just use that list and submit, maybe 6 different fMRIPrep jobs. And I found this is probably the easiest way to manage my resources. But if you have more experience with Singularity, you might have your own kind of methods for improving this workflow. Does anybody have any questions from that? I can maybe include the script in the hackmd file just for everybody's benefit.
Cool. We only have 5 minutes left, but I wanted to go through because I think it's really cool. This idea of potentially building your own Docker files, because I've now started doing this and it's actually not that hard. So the first simple thing with writing your own Docker file is that the first line of a Docker file is from a base layer. So Docker files, So when you want to create a Docker, you literally create a file that's called a Docker file, capital D Docker file. And it's usually good to create it in an empty repo, in an empty folder, because when you go to build it, everything that's in that folder gets put in the Docker. So usually you have an empty folder with a file called Docker file in it. And inside that Docker file, the first line is usually always from, and then the name of the base image. So you can, and then in order to build it, you just cd, or you just put yourself in that directory and you type docker build. T is for the name of the Docker. You name the Docker, and then a dot to say to build it from the current directory. So you can actually do a lot very quickly by just making your base layer something that's very complicated that someone else has already built. So sometimes what I do is actually I make the base layer the version of fMRIPrep that I was working with from preprocessing, and then I just add, say, Jupyter Lab or Jupyter into the base layer, and then I get a really fancy Python environment. I might add some extra Python packages, but inside that container I have all of the neuroimaging tools that were used in the fMRIPrep pipeline already set there, and that's everything. Another thing for people who work with R, the Rocker project has built all of these amazing base layers that you can use in R that are really easy to work with. So you just make the newest version of Rocker. In this case, this is Rocker with the entire tidyverse installed, and then you can just add a couple lines to install the R packages that you might want on top of the tidyverse, and you have like a really solid base layer, a really solid Docker that should actually build and run. And actually, the cool thing is that you don't actually even need to build it yourself. You can actually configure Docker Hub to build the Docker for you. as long as you actually put your Docker file in a GitHub repo, it's actually really easy. That's actually how these run, to actually sign into Docker Hub. I think you can sign in with your GitHub credentials. Click on a click repository button, and in a few point and clicks, you can actually connect your GitHub repo, the Docker file in your GitHub repo, to Docker Hub. So Docker Hub will actually build the Docker every time you push to the repo, and you don't even need to think about it. Your Docker Hub version just automatically updates every time you change the file. And in this way, you don't even need a computer to build the Docker on, which can be really useful. And then you can use that Singularity build to actually get that Docker onto Signet. Another helper for building Dockers is actually the NeuroDocker project, which I talked about, which was one of the things that I talked about in the examples. Pull. It's actually a Python package that can run in a Docker that you can use to write other Dockers. And for neuroimaging tools, it has all of the flags are essentially relate to what you would want to what neuroimaging software you want installed in the Docker. So you actually just run this Python tool, and it just actually dumps all of the text put in the Docker file into the terminal, or creates the Docker file for you. So this is an example of using a NeuroDocker to actually just build something that has FSL installed. Okay. Oh, and one last thing. This is a bit complicated, but I learned it yesterday, or I learned it last week, and I'm kind of proud of it because I realized it's very useful for me. I don't know how useful it would be for other people. But you can actually have either RStudio or Jupyter running from inside your Singularity container, inside your debug job, and then you can use port forwarding to connect to it. And maybe this is only exciting for me, but I realized that this was a really great way to actually interactively build something that uses all of the compute resources of the Niagara node, while being able to use like a Jupyter or an RStudio Jupyter or the RStudio environment while I'm in a debug job, and I still have access to like all 80 CPUs of a Niagara node. So I'm really excited to actually try this out. And I think that's, oh, wait, we're coming back. I think that's actually where we wanted to end it today. We wanted to give you a reminder to please fill out the survey, because the survey is so useful to us, and it's in your test. It should be in the test folder for this course. And that is all I need to say. Do we have any additional questions? Because we're actually past the hour, but any questions before we leave? Okay, Rook. Yes, actually, definitely. Yeah, so actually, so if you have, so Rocker is what you use to create the, so sorry, the question is, do you recommend create a Rocker if we want a reproducible R project, or create a Singularity with R in it? So it's actually the same thing. So you use Rocker, which is a project from I think the RStudio people, to actually, you use Rocker to create the Singularity image with R in it. So Rocker is the tool that you use that makes it a lot easier to actually build a Singularity image with R and all of your packages inside. Cool. Okay. Yeah, and Rocker, yes, and Rocker is very cool because it automatically installs not just R, but RStudio into that container. So you can actually have an RStudio debugging environment that you can use and connect to Signet, which is nice. So with that, we're a little bit late, so I think we'll close the class. Please do comment on the survey, and thank you so much for joining us all the way to the end. So thank you.
Thanks, everyone.